Okay, so let's just start with a recap of last week. Last week I introduced a paper by Jeffrey Hinton, and it was about distillation. And distillation is a form of transfer learning. And the main objective of distillation is not to improve performance, but it is actually to gain knowledge with what they call a cumbersome model, and use that knowledge to train a less cumbersome model or another model which cannot achieve as high accuracy, but that has some interesting properties. So we'll see that later with the decision trees compared to neural networks. But for the sake of the recap, let's just keep it a bit general. So let's say we have one function f. So if we have our training data, and we can put that through a function f of the training data and a bunch of parameters. So let's call this theta f, which are the parameters of f. And then that is going to produce a set of labels for us. Let's say it's a classification problem. So these labels are actually a probability distribution. So it's the probability of y given the data and the set of trained parameters, okay? Now f has some interesting properties, which is that it can generalize well, it can learn from massive amounts of data, and it has some uninteresting properties, like for example, it's too heavy to deploy in a mobile phone, for example. So if you imagine that you need a massive infrastructure to train f and to evaluate f, but that cannot be deployed into a smaller device, then that is a good case for distillation. So f is trained as you would normally train a machine learning model, and before distillation, let's assume that that model is trained and that it can produce a set of probabilities. So not only, also this is a vector over your classification classes. Okay, so instead of having a one-hot encoding of your classes, so it's not going to be, let's say you have 3 classes, instead of having a one-hot encoding, you have the output of a softmax function, for example, which will give you 0.25, 0.5, and then 0.25. And then this is going to be what we are going to call the soft targets. Okay? And now we have a second model which can learn from the same data, and we're going to call it G of the data, and it has a different set of parameters. And it can produce, again, another, so we call this y of f, it can produce a set of labels from G, which are actually a probability distribution of y given the data and the set of parameters. Okay? So G is going to have a different set of properties. So the interesting properties of G is that it's a small model, it's deployable, it can work very fast, but it cannot achieve as high a performance as f, either because it doesn't have enough parameters in it, or because it's a simpler model. So if you compare a neural network with a decision tree, so that one is not going to generalize as well. So the question is, can we transfer the information learned from f into G? And what we presented last paper is that the last week's paper tried to argue that yes, you can, and it's through a process called distillation. Now there are 2 ways to do distillation. So one is you have a training set for f. So you have your x train, which is a label data set. So you have x train and y train. You train f on that, and then you have a second data set, which we will call the transfer data set, called x transfer, which can be unlabeled. So this is, which normally is unlabeled. So what you use is you use f to create the labels for x, and then your loss function so G is trained on x transfer with the labels produced by f, and your loss function is the cross entropy between the soft targets, so between f of x transfer and the parameters f which have been learned. The cross entropy between that and the output of yg. Okay. What last week's paper showed is that this transfer set can actually be very small compared to a training set, which means that this model can be trained very quickly or can be updated very quickly. They showed that with something like 1% of the training set, you can achieve comparable performances. The argument of why that works is in the paper, but let's just assume that it works. And it's because of these soft targets. The other thing that they argued in the previous paper is that there is another form of distillation, which is to actually use the hard labels as well. Okay, so you create a cost function. So now your transfer set can be your training set as well. So you train and transfer on the same set if you can do it. Let's call this distillation 1. And distillation 2 uses the training set, which also has the labels, and that one is your transfer set as well. Okay. What you do is you create your loss function as a weighted average. So let's call it of two cross entropies. So the first cross entropy is going to be the cross entropy of Y and the hard targets. So let's call them Y, so they're Y train. So between YG and the hard targets, so Y train. And the second is the cross entropy between so YG and the soft targets. So F of Y train. Oh, sorry, F of X train. Strain on the parameters F. Okay?
Is that YF simply?
Is this YF?
After the comma.
Yeah, YG and YF. Yeah. It's just to wait, I just want to
Yeah, I get it.
Yeah, I just wanted to be clear that this model is trained already, so these parameters are not being learned in distillation, they are learned previously, and then they are, so this information is distilled into the other model. And that's why they call distillation, and what they say in the previous paper is that this one actually works a lot better than that one. So they argue that this loss function, is actually making G learn at the same time the hard targets, so get the correct value, and also get the correct values for the rest of the distribution. If you're using softmax as an output layer, then when you're training, you put a high temperature on the softmax, and what the high temperature does is it makes these smoother. So if you think at temperature 1, let's just at softmax temperature 1, this can be 0.01, 0.98, and then 0.01. And then if you t equals 1, that might be the soft target. If you do t equals 10, then this is going to become a lot more regular, right? And then if you continue increasing the temperature, then this becomes softer and softer until it looks like a flat distribution. In reality, you need a value of about 2 to make these hard targets softer, but not too soft that the models can't learn. Okay. So that is the whole idea of distillation. It's a very simple idea, and the spirit of the previous paper was that you can use this to train a cumbersome model and then a not cumbersome model. This paper it targets